Thank you very much for the introduction. I'm Shaikh Tousif from University of Texas at Arlington, and I'm here to present a paper titled Design and Optimization of an Electrostatic Energy Scavenger for Low Power Electronics. In this paper, we designed electrostatic scavenger which incorporates both gap closing and overlap type capacitors. I'll just go with a small introduction how electrostatic energy scavenger works. Like, it works on the basis of relative motion between parallel plate capacitor. It's actually a variable capacitor structure where the overlapping area or the separation between the plates or both will change, would vary due to the relative motion, causing a change in the capacitance, which can be conditioned to get useful power. Some of the common topologies for these variable capacitor structures can be out-of-plane gap closing type capacitors where the proof mass moves out of plane, and in-plane overlap type capacitors where there is an in-plane motion causing the overlap area between the fingers to change and therefore capacitance to change. And in-plane gap closing type capacitors where there's an in-plane motion in this horizontal direction that causes the gap between these adjacent fingers to change and causing the capacitance to change. So the whole idea is like how the electrostatic energy scavenger works is it uses vibration energy from the ambient to produce useful power which can be stored to power small electronics. And some of the vibration sources with peak acceleration and the frequency at the peak acceleration can be kitchen blender casing, HVAC vents in office building, and these are the peak acceleration they give, and this is the frequency of the peak. And we can see that these all vibration sources are present in our environment, and they're actually low-level vibrations. So the goal of this work was to design an electret-based electrostatic energy scavenger which can be used to generate power or energy using these low-level vibration frequencies. General model for electrostatic energy scavenger can be shown by this mass spring damper system where proof mass oscillates due to an external vibration, and the proof mass is supported by springs, and there is mechanical damping and electrical damping. And this system can be expressed by a second-order differential equation. And maximum power for such devices usually occurs when the natural frequency of the device matches the ambient vibration frequency. So this can be taken as a kind of an initial guideline where you design your device so that it resonates at the ambient vibration frequency. So my device was built using the CoventorWare software, and the solid model shows like this is a SOI based system. So there's a handle layer, an aux layer, and device layer, and this is the top electrode, and the proof mass is suspended by 12 springs. So gap closing capacitance forms between the top of the proof mass and the top electrode. So hiding the top electrode actually shows a clearer view of the proof mass, and with movable fingers all around it. Zooming into this point shows us the movable fingers with the proof mass and fixed fingers coming out of the sidewalls. Overlap type capacitance forms in this area. So a cross-section of the device can be used to explain the device further. So this is the proof mass with movable fingers around it and fixed fingers coming out of the sidewalls and the top electrode. And the direction of motion is in Z direction or out of plane. And during modeling, all downward motions were taken positive, considered positive. And the total capacitance and the mechanical damping present in the system are given by these two expressions, where the gap closing capacitance forms between the top of the electrode and the top of the proof mass and the top of the electrode, and the corresponding mechanical damping is a squeeze foam damping. And overlap type capacitance forms between the movable fingers and the fixed fingers coming out of the sidewalls, and the corresponding mechanical damping is the slide film damping. For the slide film damping, the distance between the adjacent fingers remains fixed as because there is no in-plane motion. However, the overlapping area changes as the proof mass oscillates out of plane. Now, the expression for the total capacitance can be used to derive the voltage and the electrostatic force equations. And after we obtain these equations, they can be used, and Kirchhoff's voltage law can be applied to the equivalent electrical circuit of the electrostatic energy harvester to obtain the overall dynamic model of the system. And spring design is also very important, as we can see that the resonant frequency of the device is related with the spring constant. As mentioned before, our proof mass is suspended by 12 springs, and 12 springs were designed to achieve an overall spring constant of 0.78 Newton meter in the z direction, and each spring is a combination of a serpentile spring and a fixed beam. So these are the equations for used to obtain spring constant for the serpentile spring and the fixed beam. So the system was designed, optimized in MATLAB using pattern search method to maximize the average power given by this expression, and the average power is a function of certain design parameters subject to two constraints. We kept the ratio of the length and width of the fingers less than or equal to 30, and we made the ratio of the length of the proof mass and width of the proof mass made equal to 6. These are the optimization results, and we can see that constraint 2 and constraint 1 both are satisfied, and the top electrode is around 13.5 microns above the top of the proof mass level. So here's a simulation. We simulated our system with a sinusoidal vibration source of magnitude 9.8 meters per second square with a frequency of 120 Hz, and we obtain an average power of 0.11 nanowatt, which is an equivalent energy density of 31 nanowatt per and 31 nanowatt and 322.78 microwatts when normalized to respect to volume and magnitude of acceleration squared. So here's the simulation result for the displacement and power versus time plots, and we can see that the displacement is a nice sinusoidal response with an amplitude of around 7 microns. So it's not touching the top electrode, not the ground. So modal harmonic analysis was also performed using CoventorWare software. It shows the generalized displacement of each individual modes with variation of frequency, and from here we can see that our mode 1, which is the desired mode, is of 4 orders of magnitude higher than the next closest mode, and the peak is occurring at 120 Hz. This actually verifies our spring has been designed perfectly to achieve a resonance of 120 Hz. Here is a short video that shows how our proof mass should be oscillating. So the top electrode is hidden so that we can see how the proof mass should be moving. So I'd like to conclude my work. SOI-based electric charge electrostatic micro energy harvester was developed. A set of serpentile and fixed spring was designed to achieve the required spring constant and achieve resonance 120 Hz for everyday vibration. And optimized system was capable to deliver a power density of 31 nanowatt per cm cube for an electrode voltage of 1 volt and capacitance of 1 picofarad. Having said all this, I would like to conclude my work. Thank you.